So we will be moving on to our next chapter, and we'll be talking about statistics. Um, statistics. Statistics is one of the most commonly used branches of mathematics in everyday life. And you hear the news, you read the paper, look at magazines, and you see statistics everywhere. And so we are going to spend a little bit of time getting comfortable with some of the vocabulary and some of the formulas and how to use statistics a little bit. Um, Section 14.1 and 14.2 is what I will be covering in this video, and it's very important that you read your textbook to get comfortable. There's a lot of vocabulary in this, and that's mainly what we're going over. And you really need to read those sections, Section 14.1 and 14.2, and then watch the video and then read the sections. Either way, they'll help you get more familiar with this material. A lot of vocabulary. So when we are using statistics, we are interested in the population. So it's the collection of individuals or objects about which we are interested in. The individuals can be people, animals, plants, objects, etc. Um, Enumeration is what we're working on right now, and so sometimes one of the things that we're interested in is what is the population size, the size of the population, and that is the n value. Um, so if we're interested in something, in learning something about a population, one way of figuring out what we are trying to figure out is by taking a census, collecting data from every member of the population. This is not always practical. Um, you may this is 2020, and every 10 years this country does have a census, and its intent is to collect to count every single individual, and then from there we also gather other pieces of information, but from everybody. When you do it from everybody, it's called a census. So since that is not always practical, uh, the study of statistics is focused a lot along the concept of a survey. And so a survey is when you're collecting data from some members, a sample, to draw inferences about a population. So you guys are familiar with this and in everyday life. In this class, um, I don't grade every single problem that you do. I would like to know how well you are doing. So I just take a survey. I pick one problem from each section. And one of the things that you figure out in taking this class is you figure out that your sample doesn't have to be huge. It just has to be representative of the population, and then you can get an accurate description of the population. Uh, So a sample is just a subset of the population. So in the context of your homework, I take a sample, I pick one problem from each section. There's different ways of collecting that sample. Sampling, the act of selecting a sample. Um, Now, when you create a sample, you're going to measure something, and a measure that comes from that sample is called a statistic. So a statistic is just a number that describes a sample, and you're going to then draw some inferences about the population from that statistic. A parameter is a number that describes a population, typically an unknown quantity. So typically what we're going to do is we're going to take a sample to tell us something about the population. So we're going to use a statistic to figure out the value of a parameter. One sample estimation. Suppose we have a general population of known size, P, and we want to find the n value of a subpopulation having some specific characteristic, for example, being a defective light bulb. So we have a general population of known size P, and we want to find the n value of a subpopulation. So what we're going to do that is we're going to choose a sample of size n. We're going to count the number of individuals in that sample having the particular characteristic k. And then we're going to set up the proportion that the proportion of k to n, the number of objects in the sample to having that characteristic divided by the how many people are in that sample should roughly be in the same proportion uh, as in the general population. The population size n divided by in, the number the total population. Okay. We can only estimate the n value of a subpopulation using a sample if we know p, the size of the general population. In many real-life applications, we don't. Okay, so let's go over how we can apply this, a very simple problem. As part of the 6th grade class project, the teacher brings to class a jar containing 200 gumballs. So this 200 gumballs is the entire population of gumballs of two different colors, red and green. Brianna is asked to draw a sample of her own choosing and estimate the number of red gumballs in the jar. Right, so Brianna draws a sample of 40 gumballs, of which 14 are red and 26 are green. Use Brianna's sample to estimate the number of red gumballs in the jar. So we want to estimate the number of red gumballs in the jar. Okay, so going back to our vocabulary of what we're looking at here. So choose a sample of size n. So the size of the sample is n. So n in this problem is Brianna draws a sample of 40 gumballs. So n is 40. Count the number of individuals in that sample having the particular characteristic k. And so then what we're looking for is the number of red gumballs. So k is from her sample. How many red gumballs do we have? 14 are red. Okay. And then P, capital P, is the size of the general population. So capital P, as part of a 6th grade experiment, the 6th grade class project, the teacher brings to class a large jar containing 200 gumballs. So capital P is 200. And then what we don't know is the size of the subpopulation. The subpopulation is the number of red gumballs. N is what we don't know. And so then the ratio of 14 to 40, there were 14 red gumballs in our sample of 40. Should be the same thing as the ratio of red gumballs, which we don't know, to the total population, 200. And then by just multiplying both sides of this equation by 200, we get an approximation. And again, this is only an approximation, but 200 times 14 divided by 40 works out to be 70. So this worked out very nicely. If it hadn't, we would just round it off. So there's approximately 70 red gumballs out of those 200. Okay, let's go through another example of defective light bulbs. Imagine you are quality control manager from a light bulb manufacturer. The light bulbs come out of the assembly line in batches of 100,000. The manufacturer's specs are that if the batch has more than 2,500 defective bulbs, 2.5%, the batch cannot be shipped. So you can see here that a lot of the times your ratios are written as percents. That's why it's very important that you understand percents. In this situation, the population of interest consists of the defective light bulbs in the batch. But testing the entire batch of 100,000 to enumerate the defectives is too time-consuming and expensive. Instead, you have a sample of 800 selected and tested. Out of the 800 out of the 800 light bulbs tested, 17 turn out to be defective. So since you have a defect rate of 17 out of 800 in your sample, you can assume that this is approximately the same thing as the number of defected in your entire number, which you don't know how many are defective, but you do know that there are 100,000. And then you can solve this proportion to get that n is equal to 2125. We can now estimate the total number of defective light bulbs in the batch by assuming that the proportion of defectives in the entire batch is approximately the same as the proportion of the defectives in the sample. So we have our proportion 17 to 800 is approximately n to 100,000. Solving for n gives an estimate, i.e. a statistic of n is approximately 2125 defectives in the batch, well under the allowed quota of 2,500. So this 2125 is a statistic because it came from a sample. And this is our best guess as to what the population size is. Finding the exact n value of a large and elusive population can be extremely difficult and sometimes impossible. In many cases, a good estimate is all we really need, and such estimates are possible through sampling methods. The simplest sampling method for estimating the n value of a population is called the capture-recapture method. So let's go through how we go about using the capture-recapture method. Step 1, capture, get a sample. Capture, choose a sample of size n. Tag, mark, identify the animals, objects, people, and release them back into the general population. After a certain period of time, capture a new sample of size n2 and take an exact head count of the tagged individuals, i.e. those that were also in the first sample. Call this number k. Step 3, estimate. Set up the proportion that the ratio of the tagged k to the total n2 should be the same for the two populations, and solve for n. If needed, round to the nearest whole number. The n value of the population can be estimated by n is approximately n1 times n2 divided by k. You're just solving this proportion right here, multiplying multiplying both sides by n and then by the reciprocal of n2 over k. But you don't need to memorize this formula, you can just derive that on your own. But notice what everything is here with all these letters. It's kind of hard to remember what everything is. Okay, so again, where did n1 come from? Capture and choose a sample size of n1. So n1 was the original number of animals or objects that were tagged. Okay. After a certain period of time, capture a new sample size n2 and take an exact head count of the tagged and individuals. Call this number k. And so then what you're doing here is you're just comparing. The way I like to remember this all this looks more complicated than it is this is the tagged to total. You know that in total, n1, which is the number of objects that you tagged already, this is the tagged. What you don't know is how many are in the entire population, and this is the total. This is what you want to estimate. And n2 is in your second sample, size, how many did you collect? Right? And so then there you go. I like to keep this in mind as just tagged to total instead of k over n2 is approximately n1 over n. That's just complicated to remember, but tag to total seems pretty simple. Okay. The capture-recapture method two-sample estimation is based on the assumption that both the captured and the recaptured samples are representative of the entire population. The proportion of the tagged individuals in the recapture sample is approximately equal to the proportion of the tagged individuals in the population. So the tag to total ratio should be the same. A large jar contains an unknown number of red gumballs. So let me try and keep these. K over N2 is approximately N1 over N. K over N2 is approximately the same as N1 over N. So a large jar contains an unknown number of red gumballs and 150 green gumballs. As part of a 7th grade class project, the teacher asks Carlos to estimate the total number of gumballs in the jar using a sample. Okay, so what we're really trying to get at is the total number of gumballs, not of red gumballs, but of gumballs. So this is what we're going to call N. N will equal the number of gumballs in the jar. Okay. N1 is in the entire jar. We know that there are 150 green gumballs. So that will be the tagged. So that will be your N1. So a large jar containing an unknown number of red gumballs and 150 green gumballs. So these will be the tagged. This is the total. Okay. As Carlos draws a sample of 50 gumballs, so then N2 is 50, of which 19 are red. Ooh, I'm sorry. Of which 19 are red. There we go. And 31 are green. So I should have been more careful with my labeling. So, and 150 green, so the tagged is which gumballs are green. So N1 is 150, which is the number of green gumballs. And so then that's the total, right? That's for the entire population. And K is for your sample, how many are tagged in your sample. And in your sample, we're keeping track of the greens, not the reds. Got to be careful with that. I just made a mistake there. So K is 31 green gumballs. And then we can set up our proportion. In our sample, we had 31 green gumballs out of, well, Carlos draws a sample of 50 gumballs. And this should approximately be the same as in the entire population. There are 150 green gumballs, and we don't know how many are green. So, but we are going to assume that they should be in the same proportion. That's why we're able to set this proportion. We could then find the cross products, cross multiply. We can multiply this one times this one and this one times this one. And then that then gives me 31n will equal 5 times 150, so 50 times 150. 50 times 15, 5 times 15 is 75. Do that in my head, and they both have a 0, so we add 2 zeros to it. And so then, to figure out what n is, we just divide both sides by 31. And so then n is equal to 7,500 divided by 31. And the calculator tells me that this is 241.935. Okay. So this is only an approximation, so you can round off to wherever makes sense to you. You can round it off to the nearest whole number. That would perfectly be fine. So n is 242. You could round it off to 240. Round it off to the tens place, whatever seems reasonable, because this is just an approximation. I'll go ahead and round it off to the nearest whole number. And so we will get 242. Estimate the number of gumballs in the jar. And although we did not run through and collect some animals, tag them, and then release them, and then let them mingle, and then recollect the animal and take another sample, you can see that the same calculations are going into effect, just looking at the problem in slightly different ways. Again, the important thing to do is to recognize what are your variables, right? So N1 was the number of green gumballs. That's how many you know are tagged in the entire population. N2 is the size of the sample, and then K is the in that sample how many were tagged. And so both of these ratios are the ratios tagged to total, and we're assuming that they are in the same proportion, same ratio. Okay, so let's move on. Let's see how this is used in the field in some biology. So a large pond is stocked with catfish. As part of a research project, we need to estimate the number of catfish in the pond. An actual head count is out of the question, short of draining the pond. So our best bet is the capture-recapture method. Step 1. For our first sample, we capture the predetermined number N1 of catfish. Say N1 equals 200. The fish are tagged and released unharmed back in the pond. So N1, this is of the entire fish population, how many are tagged? So there's 200 tagged. So N1 is 200. After giving enough time for the released fish to mingle and disperse throughout the pond, we capture a second sample of size N2. So N2 is the size of your second sample, and those we can check because there's only 200 of them. We can see how many are tagged. So N2 is going to equal, while N2 does not have to equal N1, it's a good idea for the two samples to be of approximately the same order of magnitude. Let's say that N2 is 150. So we collect 150. Of these 150, we could easily count to see which ones are tagged. Of the 150 catfish in the second sample, 21 have tags. So then that's my K. K is equal to 21. And so then N, which is the number of, so the ratio of tag to total is 21 to 150, should approximately be the same thing as the ratio of tagged to total, and there are 200 tagged in the entire population, and we don't know what that is. So then cross multiplying again would give us 21n is equal to 2 times 15 is 30. But then we have 3 zeros to add on to this. And so we have 30,000. And so then when we take the 30,000 and divide it by 21, we get that n is equal to 1428.57. And again, there's no point. Um, what should make sense is to round this either to the nearest whole fish or to the nearest tens. 1430 would be fine. I'll go ahead and write 1429. So assuming the second sample is representative of the catfish population in the pond, the ratio of tagged fish in the second sample, 21 to 150, is approximately the same as the ratio of the tagged fish in the pond, 200 to n. This gives the approximate proportion. Solving for n, we get 1428.57. Obviously, the value n equals 1428.57 cannot be taken literally since n must be a whole number. Besides, even in the best of cases, the computation is only an estimate. A sensible conclusion is that there are approximately 1,400 catfish in the pond. If I don't tell you where to round, you can round to wherever you think is reasonable, but of course, you really could not round to the tenths place. That wouldn't make sense in the context of this problem. But the ones place, the tens, or the hundredths place would be fine. Okay, so we're done with section 14.1. Moving on to section 4.14.2. Really, you hear statistics all the time, and the statistics, the numbers that you hear themselves are only part of the problem, or I'm sorry, are only part of the picture. And sometimes what I think is even the most important part of the picture is how do they come across those numbers. And so in section 14.2, we're going to talk about censuses, surveys, polls, and studies, and hopefully get a better, give you a better way to analyze the numbers that you were told. Surveys and sampling. The practical alternative to a census, collecting data from the entire population, is to collect data only from some members of the population and use that data to draw conclusions and make inferences about the entire population. Statisticians call this approach a survey or a poll when the data collection is done verbally, asking questions. So a poll, what's the difference between a survey and a poll? Well, a poll is when you are asking questions to collect your data, your information. The subgroup chosen to provide the data is called the sample, and the act of selecting a sample is called sampling. Surveys and sampling. Ideally, every member of the population should have an opportunity to be chosen as part of the sample, but this is often impossible. So every time you run some kind of a experiment, you have a target population in mind, and ideally, you would want your sample to come from the target population, and you would want everybody to have an equal chance of being in your sample. So this picture here, where you have the target population, that's the people that you're interested in finding out information about. But where you're actually going to get your information from is called the sampling frame. And what you should notice about this picture is that not everybody in the target population has opportunity to be in the sampling frame. So the target population for which the survey applies. The sampling frame, the actual subset of the population from which the sample will be drawn. So not everybody is going to be in the sample, otherwise it would be a census. And where you're going to get your sampling, where you're going to get your sample from is the sampling frame. So sometimes that's dictated by how you're going to conduct your experiment. If you're going to conduct your experiment by calling people, then your sampling frame is leaving out people who don't have a phone. If you are going to conduct your experiment by sending out emails, then your sampling frame is leaving out people who don't have email accounts. And so that's how that could happen. The basic philosophy behind sampling is simple. A sample should be representative of the entire population. Right? Everybody agrees to that, but exactly how you go about that isn't obvious. Bias, when an advantage or disadvantage is given to some portion of the population. Selection bias. Some members of the population have no chance of being included in the sample. So if you are running a survey over the phone, people who don't have a phone aren't going to be able to be in your sample. If you're running your survey via email, people who don't have an email account are going to have no chance of being in your sample. Sampling bias. Not every member of the population has an equal chance of being included in the sample. Okay, so next we'll talk about some different types of sampling. One commonly used shortcut in sampling is known as convenience sampling. In convenience sampling, the selection of which individuals are in the sample is dictated by what is the easiest or cheapest for the data collector. Never mind trying to get a representative sample. So if you were wanting to learn something about the uh, student population at the Madera Center, and you chose to go to the cafeteria to ask people questions, that would be convenience sampling because you're doing it because it's convenient. A lot of people go to the cafeteria, but there are people who are in the population that you're interested in, the students at the Madera Center, but they won't have an opportunity to be in your sample because they never go to the cafeteria. They bring their lunch from home, or they um, are running from school to work and never visiting the cafeteria. Examples: interviewers set up a fixed location such as a mall or outside of a supermarket and ask passersby to be part of a public opinion poll. So this is convenient sampling. It's convenient, it's easy, but you're going to leave people out who don't go to the mall or don't go to that particular store. Area code 800 polls. Call 1-800-U-NUTS to give your opinion on the new tax proposal. So area code 800 polls. It's easy. You're going to put up a sign and ask people to call, but that is going to create a lot of bias. This type of sample is based on self-selection. It consists of those individuals who volunteer to be in it. This causes self-selection bias, right? So in these types of examples, only people who generally, not only, but mostly people who generally feel strongly about something are going to be the ones to respond. And there's a lot of people who aren't as passionate about the particular thing that they're being asked to respond about, who aren't going to respond. And so this is going to be biased. Right now, a lot of students run to ratemyprofessor.com to see what people are saying about them. I'm sorry, about the instructor that they're going to take. And this type of information is pretty biased because only the people who, or I shouldn't say only, mostly the people who are really in favor of the instructor or really dislike the instructor are going to report. And then that gives you a very biased view of the instructor. So self-selection bias is very common and should be avoided if you want an accurate picture of what's really going on. Convenience sampling is not always bad. At times there is no other choice or the alternatives are so expensive that they have to be ruled out. However, data collected through convenience sampling should always be scrutinized. Next type of sampling we're going to talk about is quota sampling. You want your data to be representative of your population. So quota sampling is when you are going to design a sample that that has a certain number of people from certain different groups. So quota sampling is a systematic effort to force the sample to be representative of a given population through the use of quotas. The sample should have so many women, so many men, so many blacks, so many whites, so many people living in urban areas, so many people living in rural areas, and so on. The proportions in each category in the sample should be the same as those in the population. The main problem with quota sampling is that it is impossible to account for every statistically significant detail and characteristic. So I think one of the agreed upon methods of sampling that tends to work out well because it takes out a lot of bias, takes out a lot of human nature, is a random sampling. A random sampling method uses randomness as a part of the design so that any sample obtained is by chance. A simple random sample is the most basic form of a random sampling and is based on the principle of the lottery. Any number has an equal chance of being selected from a single set of numbers. So in here you have your sampling space, which is going to be the entire population, and you're going to pick some of those out. And the last type of sampling is called stratified sampling. And an alternative to simple random sampling, stratified sampling breaks the sampling frame into categories called strata. A random sample is then chosen from these strata. Stratified sampling is typically used in public opinion polls. So you break up your population into different strata, and then from each strata you randomly select people. And so this is different than quota because you're not agreeing that you're going to have certain many of these. You're just making sure that you're going to get a representative sample by ensuring that you have people or elements from different groups. So not a fixed number from each one. So here in this picture, we have a low income group, a middle income group, and a high income group. And we're going to take two of the low income groups, three of the middle income group, and two of the high income group, and get our data from there. So more vocabulary. Sampling proportion, the percentage of the proportion of the population represented by the sample. Sampling error, the difference between a parameter and the estimate statistic obtained from a sample. Impossible to tell, but we do have mathematical ways of approximating the error or giving bounds for the error. Sampling variability, the natural variability in the statistics obtained by different samples of same population, even when samples are chosen using the same methodology, right? So sampling variability means that not every group of 10 objects is going to produce the same results, the same statistics. And so that doesn't mean anybody's done anything wrong. It just means that there is going to be some variability. You can minimize this variability by taking a bigger sample size, but there is still going to be some variability. Okay, so let's look at number 16 and practice some of our vocabulary here. An audit is performed on last year's 15,000 student aid packages given out by the Financial Aid Office at Tasmania State University. Roughly half of the student aid packages were less than $1,000, Category 1. About 1/4 were between $1,000 and $5,000, Category 2, and another quarter were over $5,000, Category 3. For each audit described below, name the sampling method that best describes it. Choose your answer from the following. A. Simple random sampling. B. Convenient sampling. C. Quota sampling. D. Stratified sampling, and E, census. The auditor reviews all 15,000 student aid packages. All. Whenever you're doing all, that is a census. The auditor selects 200 student aid packages in Category 1, 100 student aid packages in Category 2, and 100 student aid packages in Category 3. So that's quota sampling, right? Let's see quota sampling. Quota sampling is a systematic effort to force the sample population to be representative of a given population through the use of quotas. The sample should have so many women, so many men, so many blacks, so many whites. So that's quota sampling, and that's what's going on here. We're going to have 200 student aid packages in Category 1, 100 student aid packages in Category 2, and 100 student aid packages in Category 3. The auditor reviews the first 500 student aid packages that he comes across, and that's B. It's just convenience. There's no reason behind it. It was just easy. And the auditor first separates the student aid packages by school: agriculture, arts and humanities, engineering, nursing, social science, and mathematics. 3 of these schools are selected at random and further subdivided by major. 10 majors are randomly selected within each selected school, and then 20 students are randomly selected from each of these selected majors. And so then that would be the stratified. And stratified D, stratified and quota kind of sound the same, except there's no in quota, there's no randomness associated with it. We're only guaranteeing to have this many of these and that many of those. And stratified, we're going to break it up into different groups and then choose randomly from them. They kind of sound the same, but there's some subtle differences there. Okay. Exercises 17 through 20 refer to the following story. The city of Cleansburg has 8,325 registered voters. There is an election for mayor of Cleansburg, and there are 3 candidates for the position: Smith, Jones, and Brown. The day before the election, a telephone poll of 680 randomly chosen registered voters produced the following results. 306 people surveyed indicate that they would vote for Smith. 272 indicate that they would vote for Jones, and 102 indicated that they would vote for Brown. Okay. 17. Describe the population for this survey. So remember, the population is who we are interested in, and (17A), the population is the registered voters of Cleansburg, right? Describe the sample for this survey. So 17B, what's our sample? The 680 randomly chosen registered voters. We're interested in figuring out how the 8,325 registered voters are going to vote. And so to figure that out, we asked the sample, the 680 randomly chosen voters. So the registered voters are the population, and the 680 randomly chosen voters are the sample. Name the sampling method used for this survey. So there is an election, the day before the election, a telephone poll of 680 randomly chosen registered voters produced the following results. So the day before the election, a telephone poll of 680 randomly chosen registered voters, right? So C, I would think that that would be a simple random sample. There is some bias in this, in that the only way you're going to be part of the sample is if you have a phone, and if you don't have a phone, then you can't be chosen. But it does appear to be a simple random. Let's move on to 18. Give the sampling proportion for this survey. So the sampling proportion is you had 680 people in your sample, and your entire population was 8,325. So your sampling proportion is just this ratio, and you could write it as a percent. Punch that into the calculator. 680 divided by 8,325 is 8.2%. So you are making your predictions with 8.2% of the votes, of the voters. Give the sampling statistic estimating the percentage of the vote to go to Smith. So for Smith, from this sample, we get that 306 people would vote for Smith, and there were 680 people in total. So 306 divided by 680 gives us 45%. Give the sample statistic estimating the percentage of votes go to Smith, 45%. So this came from a sample, so it is a statistic, and so from this we're going to glean that 45% of the people will vote for Smith. 19. Given that the actual election, Smith received 42% of the vote, Jones 43% of the vote, and Brown 15% of the vote, find the sampling errors in the survey expressed as percentages. Okay? So the actual minus the actual minus the calculated, 42 minus 45, is negative 3%. So let's see. The difference between a parameter and the estimate, right? So sampling error is the difference between a parameter and the estimate. So the parameter goes first, and so the parameter is what the actual one was, 42%, and so our survey had an error of negative 3%. Okay. Jones was 43%. But Jones was actually, Jones was actually 43%, and according to the survey, 272 out of 680 should have been 40%, and so they were off by 3% in the other direction there. And then for Brown actually got 15% of the vote, but 102 divided by 680, 15% of the vote is what the survey said he would receive, and so there was no error there. So there was no error there. Do you think the sampling error in this example was due primarily to sampling bias or chance? Explain your answer. Do you think that the sampling error in this example was due primarily to sampling bias? And so there's some room for error here because we're only going to call people who had a phone. Sometimes people change their phone, and so we would get some error there. And there is the possibility of chance that we would get a sample that was different than the actual population. So I would argue it's a little bit of both. Okay, so here's your homework for this section. This homework will be due next week. And today I will be holding a conference to help you with last week's work.